All right, welcome back everybody. We're going to be looking at the area of a surface of revolution. Now, this area of a surface of revolution, what it is, it's going to be based off of what we know about arc length. Now, if you go back to the previous section, you'll be able to see that formula for arc length that we derived. And what we want to use in this particular section is just a variation of that formula. So on here you have a definition that we're going to be using that leads us to these two formulas being used. One's going to be with respect to x, the other one's going to be with respect to y. Now all of this is based upon a function where this function is bounded between a and b. In other words, it's giving an interval for this function, and then we want to rotate this arc length that is being produced. We're going to rotate this about the x-axis. If it's rotated about the x-axis, then we're going to use the first formula. If it's rotated about the y-axis, well then we can use the second formula. All right. Now, how does this look like? How do we visualize this? In order to visualize this, I'm going to go back and I'm going to turn to my old friend GeoGebra. I love GeoGebra. This is my oldest friend, and we're going to use it to showcase what this means for the area of revolution. So here we are. Now I've programmed this to have this arc length here. All right. Now, is this a function? Sure it is. It's just a linear function, which is not too bad. All right. Linear function here. That's awesome. This function then sits just on the x and y plane. All right, so it sits here on the x and y plane, which is pretty good. All right, sorry about that. I actually meant to come over here and let's check this and let's make this go away. There we go. All right, so it actually sits on this x and y axis. The red axis is x, the y axis is a green one. All right, so it sits on here. It is a function, and again, it's just a specific portion of this function. In other words, it's its arc length. And what I want to do now is I want to rotate this about the x-axis. So when I rotate this, it's only going to start rotating about this red axis. And you're going to notice that when I start this rotation, check that out, it's creating this surface that I'm observing. Now I can keep on rotating just like that. All right. And if we keep on rotating, we're going to see this particular curve is carving out this surface. We are now going to be in the business of calculating that surface area. So given that one specific curve, can we then rotate it either about the x-axis or the y-axis? And in doing so, can we then calculate the surface area that is being produced? Right? Now, this should ring a bell. It should be very, very similar to finding the volume of solids by revolution. And that was a topic that was dealt with back in Calc 1. All right? So this is what we're doing. We want to calculate this area for the blue that was created when we rotated that specific function or that specific arc length around a specific axis. All right, so this is what we're looking at, and this is what we want to see. Awesome. So let's go back. All right, so now that we're back, let's go ahead and let's write up an example. And we're going to say find the exact area of the surface obtained by rotating the curve about the x-axis. And here we're going to have part A. This is going to be y is equal to the square root of 5 minus x and this is going to be for the x values being bounded between 3 and 5. Alright, so let's go through and let's put on our thinking hats and see what we can come up with. Alright, so let's take it away. So here we have some function f of x, which is the square root of 5 minus x, or in other words, it's 5 minus x to the power of 1/2. So I want to express it this way, that way I can take a derivative of this function, f prime. Taking the derivative is going to be 1/2 multiplied by 5 minus x. Subtract 1 from the exponent because we already dropped it down. That's going to be negative 1/2. And then multiply by the derivative of the inside, which is just negative 1. Alright, so this derivative now just becomes negative 1 divided by 2 times the square root of 5 minus x. There we are. It's a nice looking derivative. Now, once we have this, again, we're rotating about the x-axis and we're rotating over this interval. So when we want to find this exact area for this surface is going to be given by the integral from 3 to 5. And this is going to be 2 pi times, and then we're going to go back up here, times this f of x. Alright, and in for this f of x, we're going to have to then analyze what are we looking at for the f of x. Well, the f of x, as we're considering here, f of x is just y. So in here, it's just y, because again, this piece, f of x is equal to y. Perfect. And then we're going to multiply by the square root of 1 plus, and in here's where we need the derivative squared. So the derivative here was negative 1 over 2 square root of 5 minus x, and we need that quantity squared, and then that's all going to be dx in this particular case. Alright, so perfect. So we have all this so far. Now, given this, let's see if we can simplify this just a little bit more, because as it stands, it kind of looks a bit rough to deal with. So let's see if we can simplify just a little bit more. 2 pi, that's going to be a constant, and not only does it look a little bit rough to work with, but this y value here is kind of changing our values. We can't have two different variables. In that sense, I'm going to substitute in what the y value is. That y value is just the square root of 5 minus x. It's the value that we initially started with. And that's going to be multiplied by this particular function. Alright, so that piece was here. And then this other piece is just going to be 1 plus, and let's see, this is going to be 1/4 multiplied by 5 minus x. There we are. And then this is all just dx. There we are. It's looking pretty good so far. Alright, so let's go through and let's see what else we can do. Now, since this square root is multiplying both of these, we can actually distribute that square root into itself. So this is going to be from 3 to 5. So multiplying in, when I multiply in, I'm going to multiply the radicands together. So 5 minus x times 1, that should give me 5 minus x, plus, and then I'm going to multiply this 5 minus x times here, which is just going to give me that 5 minus x divided by 4 times 5 minus x. And if you see that, then that's going to be awesome, because now this particular case, or this particular setup, leads us into a very nice result. These 5 minus x's are going to cancel here, and it just leaves us with 1/4, which means we're going to have 5 minus x plus 1/4 inside of the radicand, and this is going to be with respect to dx. So let's see, 4 times 5, that's going to be 20, plus 1, that's going to be 21. So it's going to be 21 over 4 minus x, and that's in the square root. and this is going to be 3 to 5, and then this is going to be multiplying by 2 pi. And this is all dx. There we are. So all we do here is we use a nice substitution. So here, let's say we're going to use a u sub, and the u substitution that you want to use is going to be 21 over 4 minus x. And then you can find what the u substitution is going to be from there. If you follow the work, and I want you to keep going, if you follow the work all the way to the very end, the answer should be 13 pi thirds. All right, and again, I want you to follow that example, that work, all the way to the end. Make sure that you get that right answer. All right, if you have any questions, you can always post them up on the discussion board. So that was part A. Let's now look at part B. All right, so here goes part B. Part B, we're going to have x is equal to 1 plus 2y squared. And this is going to be for the y values bounded between 1 and 2. Nice. All right, so here we go. Let's go ahead and let's work through it. All right, so the first thing I'm going to do is that what I'm doing is I'm looking at this particular piece of information, and they're giving me y values, and they're also giving me that x is some function of y. Because they're giving me this, I kind of want to interpret this as my function that I'm going to be working with. In other words, that g of y that I want to observe right in here. All right, so let's go ahead and let's interpret that. All right, so here I have that g of y. In other words, this is x is 1 plus 2y squared. And if I take a derivative here, g prime of y, then my derivative is just going to be 4y. Nice. So that means that for my surface area, I'm going to be integrating from 1 to 2, and this is going to be 2 pi times g of y. But g of y for us, that's just the x value. I don't know if you guys would agree with that, but I would. So I'm just going to write g of y. If you want to interpret this as your x value, then by all means interpret it as your x value. All right? And then we need this square root of 1 plus the derivative, g prime of y, squared. There we are. And this is all dy. So I'm going to make my substitutions here. 1 to 2. And excuse me here, because this 2 pi is a constant, so I'm going to factor that out. So 2 pi multiplied by the integral from 1 to 2. G of y, that was our 1 plus 2y squared. There we are. So that was g of y. And now I need 1 plus this guy squared. So that's going to be 4y quantity squared, just like that. And this is all dy. There we are. It's looking good. All right, let's go ahead and let's keep going. This is 2 pi multiplied by the integral 1 to 2. This is 1 plus 2y squared multiplied by 1 plus 16y squared. And then this is going to be dy. All right. Looks pretty good. Awesome job so far. All right, let's keep going. All right, now I'm gonna go ahead and I'm actually gonna go back and I'm actually gonna change this up a bit. Now, the reason I'm gonna change this up a bit here is because I've been thinking about this incorrectly for this type of problem. It would be correct if we were rotating about the y-axis. But the question as it stands said that we needed to rotate about the x-axis. And rotating about the x-axis, we would still need our y value here to be input as just the y value itself. So in this particular case, we would still just need a y value here. And the reason for this is that if we want to view it, and I'm going to give you a really quick rough sketch here. If we want to view this sideways parabola, which is x is equal to 1 plus 2y squared, and if we're only going to restrict it from 1 to 2, then from 1 to 2, here's 1, and then here's going to be 2 somewhere here. That arc length that we're only looking at is here from 1 to 2. Therefore, when we want to rotate this, if we want to rotate it, then we need some sort of height right in here that we need to account for. That height is some random y value within this interval. And that's where this y comes into play. That's where that y comes into play. Alright, so when we're doing this, this is still going to be 2 pi times y. Alright, and this is all still going to be exactly the same. Alright, now once we do this, then this is just going to be factoring out that 2 pi multiplied by the integral from 1 to 2, it's just y times the integral of 1 plus 16y squared dy. And this now right in here turns into a Calc 1 problem. Now, the reason I knew I made a mistake is because when I wanted to evaluate that integral, the one that was left here, it looked really, really nasty, and we wouldn't be able to break it down with the techniques that we've learned so far unless we wanted to do an approximation. However, this question said that I want to find the exact area and not that I wanted to get an approximation. If I wanted to get an approximation, then we could have used Simpson's, we could have used midpoint, trapezoidal, anything like that. All right. From here, we just use a nice u substitution where u is just going to be 1 plus 16y squared, and then we can just take it from there. So here what I want you all to do is keep going once we've set this up. So I want you to keep going, and I want you to find the answer that will be pi over 24 multiplied by 65 root 65 minus 17 root 17. All right? And that should about do it. All right? That should do it for this surface area. All right? You're going to see similar examples like this coming up, right, in your exam or something like that. All right, but for now, this is what I want you all to work with. Awesome. So that's going to be it for today. So I hope you all had a good time, and I will see you all next time.